Hello and welcome to G Fun Facts Online. Did you know Earth has more than one moon? Well, sort of. We're not talking about a secret second moon locked in orbit around us. We're talking about something far stranger and more dynamic, a collection of celestial objects known as quasi-moons. These are Earth's elusive dance partners, temporary companions that challenge our whole idea of what a moon can be. They don't orbit the Earth, but the Sun. Yet they're stuck in a delicate cosmic dance with our planet that can last for thousands of years. So what are these phantom moons? Where do they come from? And why is one of them the target of an ambitious new space mission? Let's unravel the celestial mechanics of Earth's quasi-moons. First, let's be clear about what a quasi-moon or quasi-satellite actually is. It's any celestial body that takes the exact same amount of time to orbit the Sun as Earth does. This is called a one-to-one orbital resonance. For every one trip we make around the Sun, they also make one trip. But here's the crucial difference. They are not gravitationally bound to the Earth. Our moon is held firmly by Earth's gravity. A quasi-moon, on the other hand, orbits the Sun on its own slightly different path, usually one that's more oval-shaped or eccentric. It just so happens that its path keeps it in our general cosmic neighborhood. From our perspective here on Earth, it looks like these objects are tracing a bizarre, looping path around us. But this is just an illusion, a trick of perspective caused by our shared journey around the Sun. Think of it like two cars on a circular racetrack in different lanes. They take the same time to complete a lap, so they stay relatively close, but they aren't tied together. And don't confuse them with mini-moons. Mini-moons are tiny asteroids that get temporarily captured by Earth's gravity and actually do orbit us for a short time before breaking free. Quasi-moons stay outside the zone where Earth's gravity dominates, in a constant, subtle tug-of-war between our planet and the Sun. So how does this cosmic waltz even work? It's all about a delicate gravitational balancing act. The main force is the Sun's gravity, which dictates the quasi-moon's orbit. But Earth's gravity is just strong enough to nudge it and keep it in this co-orbital state. The key concept here, besides the one-to-one resonance, is the horseshoe orbit. Imagine an object in an orbit that's slightly different from Earth's. When it's closer to the Sun, it moves faster than Earth. When it's farther from the Sun, it moves slower. Let's say it's on a faster, lower orbit, and it starts catching up to Earth from behind. As it gets closer, Earth's gravity pulls on it, giving it a little energy boost. This boost pushes the object into a higher, slower orbit. Now it's moving slower than Earth, so it starts to fall behind. This can go on for centuries, until Earth, on its faster track, eventually laps it and catches up to it from behind. This time, Earth's gravity tugs on it again, but this time it slows it down, removing energy and dropping it back into a lower, faster orbit. The cycle then repeats. From a bird's-eye view of the solar system, the path this object traces relative to Earth looks like a giant horseshoe. A quasi-satellite orbit is just a special temporary phase of this horseshoe dance. Instead of making the full long arms of the horseshoe, the object stays relatively close to us, appearing to loop around our planet over the course of a year. Many of Earth's known companions are in this state, destined to eventually drift back into a wider horseshoe path. Now, let's meet some of these fascinating objects. To date, we've found a handful of quasi-moons, and each one is unique. The most famous is probably Kamoʻoalewa. Its name is Hawaiian, for oscillating celestial object. Discovered in 2016, it's about 40 to 100 meters in diameter and is one of our most stable companions, expected to stick around for hundreds of years. But what makes Kamoʻoalewa truly special is its composition. Analysis of the light it reflects shows it's made of silicate material, very similar to rocks on our own moon. This has led to an incredible theory. Kamoʻoalewa might be a fragment of the moon, blasted into space by a massive asteroid impact long ago. Then there's 2023 FW13, discovered in March 2023, This one is a champion of stability. It's smaller, maybe 10 to 20 meters across, but calculations suggest it has been our neighbor since around 100 BC and might stay with us until the year 3700. That makes it the most stable quasi-satellite of Earth ever found. Its orbit is very eccentric, swinging it out halfway to Mars and then back in halfway to Venus. A more recent discovery is 2025 PN7. Astronomers found it in August 2025 by looking through archival data. This 15 to 30 meter object has likely been with us for about 60 years and will stay for another 60. Some scientists think its velocity suggests it's a captured asteroid from the main belt, not a piece of the moon. We can't talk about these objects without mentioning 3753 Cruithne. Discovered way back in 1986, it was one of the first objects whose bizarre co-orbital relationship with Earth was fully understood. Cruithne is a giant compared to the others, at about 5 kilometers in diameter, and it follows a classic, messy horseshoe orbit that takes it about 770 years to complete one full loop relative to Earth. The list goes on, with objects like 2004 GU9, which will be a quasi-satellite until the year 2600, and 2013 LX28, which has a wild orbit tilted at a 50-degree angle to Earth's. This diversity brings us to a key question: where do they come from? There are two main theories. The first, as we saw with Kamoʻoalewa, is that they are lunar fragments. Simulations show that if a meteorite hits the moon's trailing side with just enough force, the ejected debris can be thrown into a stable, quasi-satellite orbit. The second, and probably more common origin, is the vast population of near-Earth asteroids, or NEAs. These are asteroids whose orbits already bring them close to us. Through a series of gravitational nudges from Earth, they can be tweaked into a one-to-one resonance, becoming temporary quasi-moons before their orbits evolve and they drift away again. So why should we care about these cosmic curiosities? Well, they are incredibly valuable scientifically, and they could be stepping stones for future space exploration. Studying their complex orbits is a perfect real-world test for our understanding of gravity, and their composition gives us clues about the early solar system. If they're captured asteroids, they are samples from the asteroid belt delivered right to our doorstep. If they are from the moon, they give us a chance to study material from deep within the moon without having to land there and drill. This brings us to the most exciting part. We are actually going to visit one. The accessibility of quasi-moons makes them cheap targets for space missions, requiring less fuel than a trip to Mars or the main asteroid belt. China's National Space Administration, the CNSA, is leading the way with its Tianwen-2 mission, launched in May 2025. The mission's primary target is Kamoʻoalewa. The spacecraft is set to arrive in 2026 to study the quasi-moon up close. Then, it will attempt something incredible. It will collect a sample of its surface and return it to Earth. To do this, it will use two different methods: a touch-and-go scoop and an anchor and attach drill. The samples from Tianwen-2 could finally solve the mystery of whether Kamoʻoalewa is a lost piece of our moon. After its work is done at Kamoʻoalewa, the probe will journey onward to study a comet in the main asteroid belt. The future of quasi-moon research is bright. Advanced sky surveys are finding more of these faint objects all the time, suggesting there's a whole population of hidden companions waiting to be discovered. Each one we find allows us to refine our models of the solar system and piece together the history of our cosmic neighborhood. These temporary dance partners, locked in a fleeting embrace with Earth, are a beautiful reminder that the solar system is not a static, clockwork machine, but a dynamic, ever-changing place filled with secrets. Thanks for listening to G Fun Facts Online.